Hi, my name is Yuqing Shi. My student ID is C55273334. Today, I will be presenting my experiment on understanding the solar system. What are Kepler's laws? Kepler's first law is planet moving in elliptical orbits, with the sun located at one focus of the ellipse, not at the center. Kepler's second law is that a planet sweeps out equal areas in equal times, so when the planet is closer to the sun, it will move faster. Kepler's third law shows a mathematical relationship. The square of the planet's orbital period is proportional to the cube of the semi-major axis of its orbit. This means that planets further from the sun take much longer to complete one orbit. Now let's move to question 9, where we explore the planet and moon scenario. Does the planet move as the moon orbits? Yes, the planet does move, but only slightly. As the moon orbits, the planet also shifts back and forth a little. This is because both objects are orbiting around a shared center of mass, not just the moon going around a fixed planet. In question 1, with the full setting, the star was much more massive than the planet, so the center of mass was deep inside the star. It barely moved. In question 4, even after reducing the planet's mass to half, the orbit stayed almost the same, and the center of mass was still within the star, because the planet's mass was still very small compared to the star. In question 7, after reducing the star's mass to half and shortening the planet's velocity, the orbit becomes more elliptical, and the gravitational balance changed. The center of mass shifted further away from the star, and the planet's motion influenced the star more than before, though the sun still didn't appear to move much in the simulation. The key difference of center of mass in the planet-moon and sun-planet case is the mass ratio. In the planet-moon system, the moon's mass is relatively large compared to the planets, so the center of mass is outside the center of the planet, somewhere between them. But in the sun-planet cases, the sun is so massive that the center of mass stays deep inside the sun, and the planet orbits around that. For question 11, since the distance between the Earth and the Sun is 1 AU, in this simulation, this distance spans two great squares, so the red line, which covers one square, represents half AU. Here we can see the screenshots of 4 simulations showing how a planet's orbital periods change with distance. At 0.75 AU, the orbit takes 282 days. At 1 AU, it's 360 days, just like Earth. At 2 AU, it increased to 1008 days, and at 3 AU, the orbit takes 1824 days. As distance increases, the planet moves slower and takes longer to complete an orbit. This clearly supports Kepler's third law: t squared is proportional to r cubed. When I calculated t squared and r cubed for each orbit, the ratio stays roughly consistent. This shows that t squared is proportional to r cubed, just as Kepler predicted, even if there are small differences due to rounding or simulation limits, since we cannot make sure it's perfect circle in each simulation. Now let's move to question 15 and talk about the orbital velocity in solar system. The planet with the fastest orbital speed is Mercury. It's the closest planet to the Sun and moves at an average orbital speed of about 47.9 km per second. The slowest one is Neptune. It's the farthest planet from the Sun, and the average orbital speed of it is about 5.4 km per second. This can be explained with Newton's law of universal gravitation and the equation for circular orbital velocity. Well, m is the mass of the Sun. It is constant for all planets, so the orbital velocity depends inversely on the square root of the distance. The closer a planet is to the Sun, the stronger the gravitational pull, and the faster it needs to move to stay in orbit. The further it is, the weaker the pull and the slower the planet moves. This relationship also connects with Kepler's second law, which shows that orbital speed varies based on distance from the Sun. Through this experiment, I learned how orbital motion is governed by Kepler laws and Newtonian mechanism. By changing mass, velocity, and distance in the simulation, I saw how orbital shapes and periods respond to different gravitational conditions. I also learned that both stars and planets orbit a shared center of mass, and that orbital speed depends on how far an object is from the central mass. The most important takeaway for me was seeing how theoretical laws like Kepler's can be demonstrated and tested through interactive simulation. It helped me connect the math and physics to real orbital behavior. Thank you for watching.